Good morning, my dear students. Last class we have discussed clearly what is total internal reflection. Now, in this class, we can see the applications of total internal reflection. So, the first application he has given in the textbook is mirrage. Formation of mirrage. So mirrage is an example of total internal reflection. This mirrage is an example. This mirrage is an example of total internal reflection. Or you can also say that this mirrage is the application of total internal reflection. So then we can see very clearly how does the formation of mirrage takes place, that is on a distant ground surface, and how does mirages forms in the deserts. We can see through this a very good and interesting concept. See, my dear students, when we go on a road, it appears that some water has collected on the road. That is, on a hot summer day, when we go on the road, it appears that some water has collected on the road, but actually when we get there we don't find any water. So that is on a hot summer day. In the daytime only we go and we go in a vehicles and we'll observe that at some distance place some water has collected on the road. But when we get there, we don't find any water. See in this picture, so there is some water patches or small water pools are there on the road, but actually we get that place, we go to that place, we don't find any water. It is an illusion. Mirrage is an optical illusion. It appears due to the phenomenon of total internal reflection. And similarly, inverted images. See in the diagram, this is the tree and the tree will appear inverted, and in the deserts also we see the inverted trees like how it is in the textbook, inverted trees. And similarly this water which is appeared on the road. So actually no water. What is the reason and how does it forms? We can see very clearly. Please listen to the class carefully, my dear students. So now see, on a hot summer day, so now see, my dear students, during the hot summer day, 8 just above the road. So now this is the road surface. This is the road surface, my dear students. Up to 8 just above the road surface is hot. 8 just above the road surface is hot, and 8 at higher altitudes is cool. So I'm speaking the two things here. 8 just above the road is hot and 8 at higher altitudes is cool. That is just above the road up to certain height only. This is the road surface up to small height from the road. 8 at higher altitudes is cool. This is the cool air and this is the hot air. So this is hot air. So that means that temperature of the air decreases with height. Means from the ground up to this height, if we divide this into different layers of air, so air just above the road, which is being in contact with the road, so the air molecules gets heated faster and faster in the daytime. So because on a hot summer day or on a hot sunny day, the road gets heated and the air in contact with that also gets heated. So we have a hot air on the surface of the road, and if you go up, we have a little less hot and less hot, and here if you compare, here we have a cool air. So what is the sentence he has given? So on a hot summer day, air just above the road is hot and air at higher altitudes is cool. So from ground to this height, I divided this height into different layers. So here I have cool air and here I have a hot air. So hot air and cool air means as height increases, temperature decreases. That is, temperature decreases with height. So means we are writing the shortcut. What children you see? Temperature of the air decreases with increasing the height. So now next point. So as a result, so see, density of the air so increases with height, because density of the cool air is more. This density of the cool air is more and density of the hot air is less. That's why density of the air increases with height. So it has more density, it has less density. It's an experimental proof that density of the cool air is greater than the density of the hotter air. So density of hot air and density of cool air if you consider, so the cool air density is greater. So and we also know that density of the air increases refractive index of the air. Refractive index of the air increases with density. So refractive index of the air increases with density. So refractive index of the air increases with density also, we can say that. So and this cool air has more density, you are saying, and density cool air has more density, we are saying. Refractive index of the air increases with density. So refractive index of the air increases with height also, because see what we have written, as height increases, temperature decreases. As height increases, temperature decreases. So that is, temperature decreases means density of the air increases. Density of the cool air is more than the density of the hot air. Means refractive index increases with density. That's why refractive index of the air increases with height. So density of the cool air is greater than the density of the hotter air. Means it has more refractive index. This density. So refractive index of the cool air is greater than the refractive index of the hotter air. Means it has more refractive index. This has a less refractive index. Means I can consider this as a denser medium, and I can consider the below layer as a rarer medium. And if I consider these two mediums, if I consider these two layers, this layer is denser and this layer is rarer. And if I consider these two layers, now this is denser, this is rarer. And if I consider these two successive layers, again, so this is denser and the below one is a rarer. So that's why we can say that, so this is more denser medium, and this is the rarer medium. If these two you consider, this is the denser and rarer. This is the thing happening. Okay, now that's why light travels. So here refractive index is less and here refractive index is more, you are telling. So light travels faster through this thinner hot air than through this thick cool air, because cool air has more refractive index and this hot air has less refractive index. Cool air has more refractive index, and this hot air has less refractive index. We have written, means velocity of light in the cool air is less than the velocity of light in the hotter air. So that's why, and see, due to this, now a light ray from this tree. So a light ray from this, if we observe that this is a light ray from the tree, it is passing from denser to rarer, and this is the point of incidence. Here we have drawn the normal. So denser to rarer means, so it bends away from the normal. This is the original part. It has bended away from the normal. And again also you see, my dear students, so at this point again point of incidence normal, this is denser, this is the rarer, this is the original part, again bends away. So see, this angle is increasing. Here this angle is more than this one. Okay, like this here it will come. Okay, so the angle of incidence goes on, increases from here to here. See, it has to go like this, denser to rarer, bends away from the normal, again denser to rarer, bends away from the normal. So it is suffering refraction at a particular point. This angle of incidence is greater than the critical angle. So fine, this is the denser medium, this is the rarer medium we know, and light ray traveling in the denser, angle of incidence is greater than the critical angle, so it suffers total internal reflection and it suffers a total internal reflection here. And now going from rarer to denser, and again this is what point of incidence. So rarer to denser means, so rarer to denser. So see students, it bends towards the normal, like this it will follow curved path and reaches the observer. So see, when a light from the tall object, so see my dear students, so when the light from the object, so that is on the normal day, if light travels in the straight line paths, light travels in the straight line path as shown in the diagram. So if it travels like this, nothing will happen. We can see as the same height of the object only. But due to this change in refractive indices, light from this tall object follows this kind of path. So see, when the light from the tall object, so light from this tree, light from the tall object, okay, such as a sky or a tree, it may be from the sky or the tree, passes through this medium, suffers refraction and follows a curved path due to the total internal reflection. When light from the tall object such as a sky or the tree from this passes through a medium, so when a light from the tall object, see my dear students, light from the tall object such as a tree or the sky passes through a medium just above the road, whose refractive index decreases towards the ground. This refractive index, whose refractive index decreases towards the ground, whose refractive index decreases towards the ground, suffers refraction and takes a curved path because of the total internal reflection and reaches the observer as shown in the figure. But for the observer, this light ray appears to come from here. So for this observer, the light ray appears to reflected from the ground. Means for the observer, So the light ray appears to come from here, and it gives an illusion that an optical illusion that there is some pool of water on the road. So it gives to the observer that. So see, the refracted light reaches the observer. The refracted light reaches the observer in a direction as shown in the figure. So that refracted light reaches the observer in this, see my dear students, in this direction. In this direction. So means this appears to the observer that the reflected ray reaches from the ground. So, and hence we feel the illusion of water being present on the road. So the this ray reflected from the ground, it appears to the observer that it is coming from the ground. It gives an illusion to the observer. So hence there is a pool of water on the road, which is called a mirrage. And similarly, an inverted image of the tree observed in the deserts. An inverted image of the tree observed in the deserts. It is also an application of total internal reflection. See, my dear students, the main important point here is mirages or the applications of. It's an application of. Mirrage is an example of TIR, or it is an application of total. So what is that? Total internal application of total internal reflection. It is an application of total internal reflection. Okay, students, and now see, air just above the road is hotter than the air at higher altitudes. So we have hot air here and we have cool air here. Means as height increases, so temperature of the air decreases. Temperature of the air decreases. Means we have a cool air at the top. Means density of air increases with height. And we also know that density of the cool air is greater than the density of hot air. And also we know that refractive index of the cool air, refractive index increases with density. Refractive index increases with the density of air. So means refractive index increases with density of the air. Means refractive index of. So we can write like this, see my dear students. Then refractive index of the cool air. So refractive index increases with density. So density of the cool air, as height increases, density of the air increases. So density of the refractive index increases with density. Means it is also increases with height. So it is also increases with height, because density increases with height we have written, and refractive index increases with density we have written. So that's why the refractive index, density of the air increases with height, and refractive index also increases with density. That's why density of the cool air is greater than refractive index of the cool air. Refractive index of the cool air is greater than the refractive index of the hot air. So because of this, so refractive index of the cool air is greater than the refractive index of the hot air. Means from the top to ground you reach, as the depth decreases, refractive index decreases. It is mentioned very clearly as shown like this in the textbook. So when the light from the tall object is coming, it is coming from denser to rarer, it bends away from the normal. Again denser to rarer, bends away from the normal. Like this it is coming, and here the angle of incidence is greater than the critical angle. So total internal reflection takes place. Now going from rarer to denser, bends towards the normal and reaches the observer. But if you extend this ray, it appears to come from here. For the observer, this light appears to reflected from the ground. It gives an illusion that there is some pool of water on the road. On that road, the image of the tree can be seen, or on the road we can see the sky. We are seeing the sky on the road means we are feeling that some water has collected on the road, but actually we cross that place or we go to that place, we don't find any water on the road on a hot summer day. When we go through the bikes or any vehicles, we can observe it. You can also observe it, children. I have observed many times on going on the road that is on a hot summer day. It's a natural phenomenon. It is occurring on the roads, and similarly in the deserts. When we go in a deserts and our eyes or we feel that there is some pool of water in the deserts, but actually you go there, you don't find any water in the deserts. Because so the air in contact with the deserts gets heated, and air at a bit of higher heights is cool. So the light ray from the trees in the deserts comes this curved path and reaches our eye like this. The light rays from the trees in a desert. If we are here in a desert, we are going on a camel. We are on the camel and camel is walking. We are here and there are some trees in the deserts. The light rays from the desert does not reach straight as shown in the textbook. They follow this kind of curved path. So we will find that inverted trees will appear for our naked eye. Inverted trees will appear. Inverted trees are appearing means we are feeling that there is some water, a pool of water is there at that place, and actually we will go there, we don't find any water, and the reason behind it is the phenomenon of total internal reflection, so which is called mirrage. So the next class we can see the brilliance of diamond and optical fibers. Thank you, students.